we can start our evening session. The first speaker is Wilke Schee. He will tell us about entanglement and thermalization at the butterfly velocity. Please, 45 minutes.
Thank you. Let's see, let me share my. I guess now you can see the slides. Is that right?
Yes, great.
Yes.
And
thanks very much.
You, like this.
You cannot see me, or you can?
Yes. But this is only, you will see, no, this is not you, this is me. You will see your photo in the, let's me do it.
I didn't, let's see. But the video should be on, right? Or
Yes.
so it's working fine?
Please switch on your video. I will.
No, it's working.
It's working.
It's you, yeah. So I don't see myself actually, but then,
yes, this depends on your program.
But it says
when
that it's working.
Speak, yes, it's working. When you speak, we will see only your slides and your photo and your video.
Okay, yeah, that's perfect, right?
Mm-hmm.
Yeah. So thanks very much. So of course it's too bad that we couldn't physically be at the workshop. I would have really liked to come to Moscow, but still very nice that you organized this virtual conference. So yeah, so this talk will be about entanglement formulation at butterfly velocity. It's based on this recent paper last January with Mark Mizai. And well, at the end, I guess you'll see more about all these kind of different entangling regions and entanglement entropy as a function of time and when it thermalizes at its thermal value. As an outline, so first we'll try to introduce a little bit what we know about entanglement entropy and its saturation to the thermal value. For this, I'll introduce this relatively old idea of this entanglement tsunami, where you really have this entangling region, and the entangling goes in with the entanglement velocity. I also say a little bit more about the butterfly velocity. And then most of the talk is actually about this what actually originated in like tensor networks and condensed matter communities, this membrane theory, and it's kind of in some sense a hydrodynamic approach to entanglement entropy. So you really take like a long wavelength limit and the late time limit, and in that approach you can really compute quite precisely for different shapes the entanglement entropy. And this is a one-to-one correspondence in holography with extremal services like Ryuta services. I'll briefly mention that too. And then, well, the results of this paper were was also some numerics, where we could actually compute in this membrane theory thermalization of like ellipsoids and stadii and rotated in several ways, which has an interesting results that the black holes, they thermalize fastest for a large class of shapes. So I'll actually make quite precise which black holes and for what shapes they thermalize with this so-called butterfly velocity, which is then the fastest possible. And well, I don't see any of you, but please, yeah, give some feedback every now and then if everything is clear, and ask a simple question. That would be really appreciated anytime. Okay, so this as a very quick introduction, I guess most of you are familiar with this. But to kind of set the stage, to compute entanglement entropy, we of course are very familiar with this proposal by Ryuta and Yagi, where you have like your boundary CFT and you have a region B you want to compute the entanglement entropy of. So you trace out A and you want to compute the entanglement entropy, which is the normal von Neumann entropy. And then the prescription is really to kind of find this minimal surface in ADS. And the area of a 4 is then really the entanglement entropy, where the area of 4 comes really from Bekenstein-Hawking formula. I also put this picture because, well, of course, so to make two comments. Well, first one is that I guess also most of you know that entanglement entropy is divergent because the boundary contribution is divergent. But in this work, we'll mostly be concerned about thermal entropies. So what we will be looking at is that you put a black hole, so you have like thermal ADS, and then you compute the entanglement entropy and you subtract the vacuum contribution to cancel this kind of UP divergence. The second reason I wanted to put this slide also to kind of emphasize a little bit, so this is the original proposal, it's a minimal surface. If you add time, it's kind of natural that this minimal surface becomes an extremal surface. But then, of course, it's much harder to compute for general regions. Because if you take a minimal surface, you can relax it step by step to kind of make it smaller and smaller and smaller. Typically because ADS wants to get deeper and deeper, or wants to go to the horizon. But if it's an extremal surface, then you really have to kind of, well, you can make it smaller in the time direction, and you can make it bigger in the space direction. So you really have to solve all the PDEs for general shapes. It's a much harder problem, which we'll try to address here in this hydrodynamic limit. That was as an introduction to this HRT formula, which we'll use throughout this talk, and then to kind of set stage a bit what we actually compute is this. So you quench a system, you start from vacuum, you quench it in a Vaidya way, and then you have a thermal system, and then you want to kind of, the system will thermalize, and you want to kind of really see the entanglement as a function of time. So for this, we studied also in this paper previously with Christian Ecker and Daniel Grumiller and collaborators. Here I show results for 1+1 dimensional CFT, Vaidya type quench, but later on I'll argue that it doesn't actually matter how you quench it. So these Vaidya quenches, they really have this just very standard ADS metric where this m as a function of t is a step function. So at t smaller than 0, it's 0 and it's vacuum, and at t bigger than 0, it's m equals mt equals m, and it's just a Schwarzschild black hole. So this is kind of what you can see here in this picture. So it's smaller than 0. This is vacuum ADS, and this is the thermal Schwarzschild black hole. And at t equals 0, there is this quench, and because we're using here Eddington-Finkelstein coordinates or null coordinates, this this metric is also a resolution. You really have this null shell at t equals 0 falling in these null coordinates instantaneously. So it falls in with the speed of light in reality. And then after that, instantaneously, it forms this horizon. And then to compute the entanglement entropy, in this case, it's a 1+1 dimensional CFT. So there are only two things you can do. You can take a region of a certain size L, and you can look at it as a function of time. And then you can compute these Ryuta-Kaniagi surfaces. And in this case, we could actually solve the full time-dependent problem. So the extremal surfaces. And the reason is of course that in this case, because it's only 1+1 dimension, the extremal surfaces are just single lines. And if you want to extremize a single line, that's basically equivalent to computing a geodesic. And geodesic equation is very easy to solve. But in higher dimensions, that will be much more complicated. So that's actually what drawn here. So here you actually see these Ryuta-Kaniagi surfaces, or extremal HRT surfaces, maybe I should say, because they're extremal, for several kind of separations at time t equals 2. So at time t equals 2, we're kind of here. So there's a horizon at z equals 1, and you actually you see it visually already that these HRT surfaces, they cross the horizon at z equals 1, and then here they actually cross the shell, and then they live in vacuum ADS. Of course, you from this picture is not so clear because here I only show the ADS direction and the x direction, so you don't know what the time is. But okay, since you can see here it crosses the shell, and the shell is at time t equals 0, you know that here the things are t equals 0, so it's these ones. And okay, then also these it's actually, and if you take these coordinates, then HRT surfaces in vacuum ADS, they're semicircles. So indeed, you see that these ones are semicircles, and here you would have really ADS geometry, so it would actually more or less follow the horizon. So the two things I wanted to note here is that we'll come back to is that well, maybe surprising. I guess it was first found in this paper 2010 by Esperanza Lopez, but in this kind of quench, these HRT surfaces, they actually cross the horizon, and then they also cross again the shell. And well, and then actually you have this vacuum ADS part, and then they cross the shell again and the horizon again. So there's like 4 crossings here in these colored lines. So that's one thing I wanted you to notice. And the second thing I wanted you to notice that there's all these gray lines here. And the gray line, so this is for fixed L, but then all these surfaces they start they're at a different time. So if the surfaces are before t equals 0, then it's kind of obvious that they don't cross the shell. They just live in vacuum ADS, and entanglement entropy minus the vacuum result is just 0. That's our renormalization. But for these late times, it's quite important that actually then you kind of have this time-independent geometry, and then you can actually prove that these surfaces have to stay out of the horizon. And you see also that they actually kind of want to touch the horizon. So what happens at late times is that you have a surface, especially long length limit, that really hovers around above the horizon. And that's also why at late times, as you expect, you get exactly the thermal entropy, just the A/4, the area of the black hole horizon. But okay, what I want to point out specifically is that these lines, that since they don't cross the shell, that's why they're gray, they live exactly, the whole surface lives in ADS Schwarzschild. So it doesn't know at all about this shell. And also so this entanglement entropy is exactly equal to the thermal value. So there's really like if you wish, there's like a discontinuity. Well, I'll come back to it later, but there's really like it's not that it exponentially relaxes, but it really exactly relaxes. Okay, the last part about this 1+1 with CFT, and then I'll go to more general shapes. So now we can plot this renormalized or the subtracted entanglement entropy as a function of time for several of these lengths from 3 to 7. And okay, then so more or less happens what I told you is like, for instance, for this L equals 7 at the time 3.5, exactly it saturates at the thermal value. Because then it becomes gray. And maybe here it's not super well. Here, I guess we didn't do like a delta function shell, but a small smoothed out. So it's kind of slightly smoothed out, but that's really what you see here. And the other thing I wanted you to notice is that there's this linear growth here, which I'll come back to shortly. So this is kind of the plots we are going to look at for the rest of the talk also a bit. And then the question is really like, when is your system thermal, which is in this case, for instance, t equals 7/2, so 3.5, because then everything is thermal. So how does this work for more general shapes? So this is actually this very nice paper by Hong Yu and Josephine Su of 2013, which is called Entanglement Tsunami. So for a general shape, here they ignored this early time dynamics, which is actually quite important. So there's a time scale 1 over the temperature. So there basically, if you look at these plots, there are 2 time scales. So the one is like the saturation time, so that is kind of proportional to the L. And then there's also the temperature, which gives an extra time scale. So what you actually see is that there is this linear growth, but initially it's not quite like that. So there's a time scale 1 over the temperature, where actually you can prove that this entanglement entropy goes like t squared. So actually, so what follows in the rest of the talk will ignore this t squared, and we just assume that from t equals 0 it grows linearly, which is a good approximation as long as the time is much bigger than 1 over the temperature. So that's and that is also important for other reasons, because okay, this VAIDYA case where you just have this step function and you have this null dust flying in, but people could say it's a very particular model. Why do you choose VAIDYA? But of course, you kind of expect, if you look at this metric, that any other type of quench you would do within a time of order 1 over the temperature, it would settle down also to a Schwarzschild black hole. So the statement would really be that it's kind of insensitive to what we do, because we're looking at time scales much larger than 1 over the temperature, and then it doesn't really matter how you quench this. Well, and then okay, so you have this entanglement entropy growing as a function of time, so now it really grows like linearly. This is just like as an example, a plot. And what they found is that the entanglement entropy actually grows like, well, this is the equilibrium entropy density times the area times some time, and this is then a definition, or it's kind of a characteristic scale, if you want, a characteristic speed, which they call the entanglement velocity. So you really see that basically, so the interpretation of this tsunami is that you have like this area, and if you want to know how does the entanglement entropy grow as a function of time, it's really a local process where basically along the boundary of your entangling region, you generate entanglement entropy, and crucially, and well, so actually it's a bit different here. We could have computed it. You could, if you see this linear line here, it's actually it goes to it thermalizes at 3.5, because it's a 1 + 1 CFT, and in that case, the entanglement entropy velocity, the entanglement velocity is 1. In one inch CFT, this thing thermalizes at the speed of light, the entanglement. But in higher dimensions, this is not the case, and it cannot be also because, well, even though maybe all your quasi-particles are in strong coupling, other degrees of freedom if they move at the speed of light. If you're in higher dimension, of course, they don't move always perpendicular to the surface. Some particles, they go in different directions. And also in this paper, they very nicely argue how this entanglement velocity, for instance, worked for free theories. And then they also compute it for holographic theories, and you get this relatively beautiful formula depending on how you want it, where this velocity really only depends on A, which is the metric factor. So this is C squared here in this case. It's the DTT metric factor. So if you give a black hole, then you can compute the entanglement velocity using this formula. And okay, what I also wanted to say about this is that, as you see here, of course, because the entanglement, so the entanglement of course grows because this orange region gets the thermal entanglement entropy, but then the area of this piece gets smaller and smaller. So in this case, particularly, you see, and it's also kind of expected, entanglement entropy grows slower and slower, and then it saturates at some. So this is kind of shape-dependent growth, but the initial time is linear. Are there questions about this tsunami and how this entanglement velocity? What's the interpretation of this entanglement velocity? It's kind of important. Or about the Vaidya and so on. Okay, then I just wanted to do 2 examples, and then we'll go to this more general framework, and then to more general shapes as well. Okay, so the examples are very simple. So the first one is a stripe or a region, which is this infinite transverse dimensions, and then there's a characteristics size here, R or L if you prefer. And in this case, so it's also still from this paper by Hong and Josephine, that you can compute analytically, well, it's very easy, the entanglement entropy as a function of time. And depending on this R, the separation between the 2 plates, well, I should say it's kind of it's the radius of the largest inscribed sphere. So actually, so in this case, L would be 2R because you would be able to draw a sphere here. And then R will be that radius. So it's kind of important to keep in mind. And if you have the stripe, so what they found is that there's no such thing as that, but it's kind of consistent with this picture that this area doesn't change. So there's no reason why the slope wouldn't be all the way linear. And you can actually prove analytically then it is all the way linear. So this entanglement tsunami, in the case of 2 stripes, it just comes in and then at some point it meets. And that means that at that point, the entanglement entropy is the thermal entropy. So you really see this here. So the entanglement entropy grows and it meets the thermal value 1 because I normalized the thermal value, and then it stays 1, stays thermal. And then really the derivative here is discontinuous. So that's why I call this discontinuous saturation. And then the velocity with which this happens is given by this eta formula, eta d minus 1 over d. Well, it's the same velocity as this one actually. For sphere, it's a little bit more complicated, but you can still do it analytically. And they actually have a formula there for the saturation time as a function of the radius, and it scales with the radius. And well, so first of all, first goes with the same entanglement velocity linearly, and then with the area and all that. But then, okay, so then the thing shrinks and it has to slow down. And actually you have some critical saturation here. So well, I didn't want to go into details, but it actually goes with a power law, T minus TS, with TS, the saturation of the things. And then at that point exactly saturates. It's power law, the thing going there. And this one actually saturates at the, well, they computed and they called this 1 over CE. So they didn't call it butterfly velocity, but it actually, well, because it's a time over the radius, it also has a particular speed. And it turns out, and well, so their velocity is already there, but it's actually exactly the butterfly velocity. I'll say a little bit more about butterfly velocity later on. It's 1 over square root eta. And which, well, from the picture is already clear, it's considerably faster than this stripe thing, which is like 1.6 numerically, and this is 1.25. Any questions about that? Okay, so well, these are of course interesting examples, and then we want to kind of go on and compute this in much more general. And well, maybe here I should already mention that that there is this that well, you can actually prove in holography at least that you cannot saturate faster than with this butterfly speed. So the fact that this saturates, and it really saturates at the butterfly velocity, is saturating this bound that you cannot thermalize faster. Whereas this one, of course, thermalizes later. So this is like not saturated. It's kind of the normal case, where the sphere case thermalize as fast as possible. One thing I can mention here also is that this doesn't happen in d equals 3. So it only happens in d equals 4, that it exactly saturates at the bound, which is 1 over the butterfly speed, with the thermalization of 1 over the butterfly speed. It also doesn't happen for if you go close, if you have charged black holes with a large charge. If you have small charge, then it also happens. But if you have large charge, then you cannot saturate at the butterfly speed. So since it kind of sometimes happens, sometimes not happen, it was actually so. The open question we want to study actually in this work is if this sphere case where you really saturate at the butterfly speed, is it really special, or is it a generic phenomenon? Is this kind of fast scrambling or fast thermalization? So to go to more general cases, so this is actually work that was done previous by Mark on entanglement spreading from holography. It's kind of this hydrodynamic limit of exactly this Vaidya case. That's why I spent a little bit of time introducing this case with some simple examples, where you get relatively complicated pictures like this, where you have like what is in ADS, you would have like the null shell falling into the speed of light. There will be a horizon, there will be equal time services, and then you would have, so if this corresponds to that, you would have all these kind of Ryuta-Grignani services which go through the horizon and then maybe also through the shell. And then this orange thing is between the shell and the horizon. And okay, maybe I don't really have time to explicitly show it, but I can make, I think, quite quite intuitive. I think that if you take this hydrodynamic limits, which means system size, entanglement region size much larger than 1 over the temperature and much later than 1 over the temperature, so to be consistent also with the tsunami picture. Well, first of all, I already said the details of the quench are unimportant. But what's much more important is that you don't have to compute the whole surface. So actually, so if you compute in that limit, the part of the surface outside the horizon and beyond the shell, they're negligible. And in the end, I think that's also quite intuitive, because well, outside of the shell there are these semicircles, and the entanglement entropy goes like log R. So it doesn't scale with R, but it goes like log R, because you have an ADS geometry and it's cut off at beyond the horizon scale. So it doesn't grow fast enough, and here you can already kind of see it from the picture. These geodesics going from the horizon to the boundary. Well, of course, I already said the actual area is divergent because of the UV divergence. But since we subtract the vacuum solution anyway, so we subtract the UV divergence, then the contribution of the horizon to the boundary also scales like 1 over the temperature. So it's in the long time limit and in the large region limit, it's also negligible. So in the end, what we actually only have to do is to compute the surfaces from the horizon to the shell. So that's kind of the intuition, what we're always trying to compute. So you put, well, so the region at the boundary and at the horizon, they should be, they differ a little bit by effect of 1 over the temperature, but that is then consistently ignored too. So you have like your entangling region on the horizon, and then they have to end, well, they have to be perpendicular on this nil shell. You can show that, and that's the thing we actually want to compute then and take the entanglement entropy off. Is that somewhat clearer? Well, then I don't want to go through all the formulas, but I kind of, maybe I'll just put it here for reference if you want to go to look at it later. You can actually then go from the real HRT formulas and derive this membrane action. So the thing we're actually going to minimize and compute the entanglement entropy with. But just for completeness, I want to give you a flavor like how the derivation goes. So you have like a general black hole metric like this, with some factor A, one factor B. And then since we want to take this hydrodynamic limit, it's of course convenient to rescale your variables with R, the system size. So T goes like R tau and R goes to R rho, with R a large number. And then crucially, the holographic coordinate doesn't scale. So the Z becomes zeta, holographic coordinate. And then you just write down your standard, standard profiles and your standard well, the minimal surface or the extremal surface equation, but given the scaling and taking the large R limit, and then, well, of course, because it's large R and the Z is just the zeta, then the nice thing is that if you write down your minimal surface, I mean, I don't want to kind of go through the whole thing, but it's intuitive that there's a tau derivative, there's an omega derivative, but there's no zeta derivative anymore, and that's just because it's subleading in R. So, normally you had this PDE in the holographic directions and in the boundary directions, but because of this limit, zeta doesn't have derivatives, and you can integrate it out. That's the whole idea about this membrane paradigm, and that's exactly what you do. So, okay, so we have this. Well, I just copied this from the last thing. So the zeta you integrate out. So you have your Lagrange equations for zeta, which gives you some variable which we call v squared, and v squared is really the tau rho, the omega rho, where rho is rho again is this kind of the holographic coordinates. It's the boundary coordinate. So it's R as a function of time and your coordinates, and the time, you divide the time derivative by the norm. So it parameterizes your surface, this rho, this function of time and omega. So you really have a membrane which depends on time and omega, but you have to remember in this case there's no, well, zeta is kind of solved for, it's determined, so you integrate it out, so there's no holographic coordinate anymore. So you really have just a surface in the boundary, t and t x y z, and then since this is d2 rho, so this v is really just the angle of time and the angle of your surface makes with the time axis. And that's really kind of, in this case you can treat it as a definition, but it has this very nice interpretation. Okay, and then you work a little bit further, taking this definition, and you simplify, and you find that your entanglement entropy is given by the integral over this surface of what's then called this membrane tension. So it's an angle-dependent membrane tension function, epsilon v, and that's the one you integrate. And this epsilon v is then given by square root minus alpha prime zeta, and it depends on well, zeta then depends on v. So there's zeta is integrated out, but okay, if you do it for fully general metrics, you actually have to kind of invert this numerically, but there's no zeta because the zeta is determined by v, and v is the angle. Okay, I mean, this goes very fast, and if you want to know the details, you have to look at the paper. But okay, the two things which are very important is that, first of all, there's no holographic direction anymore because of the hydrodynamic limit. And the second thing is, okay, now the entanglement entropy is the integral of this over this membrane of this epsilon v function, where this epsilon v depends on the black hole metric, but it doesn't depend on anything else. And now this is a time-like surface, and of course we still want to extremize this thing in principle. But since it's a time-like surface, it has become a minimization problem again, because the surface is time-like, so it just has a certain entropy, and then, well, so the original extremization problem becomes a minimization problem. This is very important because then we can actually do it much more easily numerically. I'm going quite fast there, but still, if you want to ask questions, you can, of course. Then just to say a few more words about this epsilon v, which is very important, this membrane tension function. It actually originated, so not in holography, so that's a nice thing. So it originated in this paper in 2018 by David Husse and Adam Nahum and Jarina Yonai. So this is their picture actually, and they really noticed that if you compute entanglement entropy, there is this certain entanglement velocity or different velocities, and that you really want to minimize as a function of this velocity, where in this case, well, normally actually this velocity, this would, in their case, 1 + 1 dimensional quantum mechanics will be straight line, but they noticed that if your dynamics for some reason depends on time, then the velocity also would depend on time, and this would be then a universal function. And they noticed that if your velocity is just well, so to say, if v is 0, then your so that it will be straight. Then indeed entanglement goes with the entanglement velocity. And they also noticed that there is this butterfly velocity. It's that also goes into kind of, well, it actually takes some effort to show in ADS, but in ADS it's also true. This is a monotonic function. which if your membrane goes just straight down, your entanglement entropy grows with the entanglement velocity. If it goes with an angle phi b, then the entanglement entropy saturates at phi b, and in between that, it's a monotonic function, assuming the null energy condition in the bulk. So you can show all these things, and how this actually. Okay, I don't think actually, and then you can of course look at all the mathematics, and this works out very nicely. That it is the epsilon at the butterfly velocity is the butterfly velocity, but this butterfly velocity has an independent definition. So the butterfly velocity is really the velocity with which chaos spreads out. So it's related to this other paper by Mark and Douglas on entanglement spreading in chaotic systems, where you take like out of time ordered correlators, you kind of do like shock, or you quench, and then you kind of look at the correlator again, and then it has this characteristic chaotic growth, which also goes at a certain speed, and that goes with the butterfly speed. But this out of time ordered correlators is more like a UV property. Of course, it's also determined by your black hole properties, but it's not easily related to this kind of, well, in this case, it's quite easy to kind of see what's the epsilon v in terms of your black hole geometry, and then determine the butterfly velocity like that. But it's not super easy to see why this kind of UV property or correlation functions are directly related to this butterfly velocity. But in the end, yeah, well, you can show it, and it's actually also probably why this is an exciting topic. Well, that was kind of my introduction on this membrane theory. So there's questions about that, and otherwise I go to the results for more general how you can actually use this membrane theory. Yeah. Okay. So since it's now a minimization problem, we really could just, well, so there's this kind of service evolver, and you can put it in a computer, and you kind of let it go for 10,000, 100,000 steps, and then you refine it, and you let it go, and you refine it, and you get all kinds of pictures like this, where really this boundary region is really this entanglement region on the horizon, as I showed, and then the thing to minimize for the service evolver, you really kind of look at the angle, and you compute the angle, you put in this membrane action I just showed you, and then okay, so then the boundary condition is that at the Vaidya dust shell, it needs to be perpendicular, and that boundary condition we just implemented by flipping the service over. So that's why you see it here twice. But in the middle, it should really be this null shell, and it should end on that shell. But this is how we do this in practice, and we minimize it. We first did like a bit of a toy model where you take like an ellipsoid. This is in 3 dimensions, so it's a bit simpler. So there's like there's an elliptical region on the boundary of 2 + 1 dimension. So it's just, and then you get like a 3-dimensional. Well, then one extra. This is then the time direction. So at early times, the distance between the distance between the horizon and the shell are not that big yet. I mean, remember that this one crosses at a certain time. On this time, well, this time is 1/temperature, so it's negligible. So you're really interested in the time between the horizon and crossing of the shell, which is t. So at early times, this distance is not so large, and actually the surface wants to be more or less vertical, which means the angle is quite almost 0, so it grows with the entanglement velocity, and that's actually also what explains this linear growth initially. And then at later times, it kind of gets more and more curved, and at very late times, it actually breaks. And it breaks. When it breaks, then the entanglement entropy will be the thermal entropy. So this is just as an example. So these are, and all these curves, okay, so I put some examples here, but all these different colors are different ratios. So R = 1 would be a sphere, and this would be ellipsoids with different ratios. And you can see all of them, they kind of, as a function of time, well, they have that characteristic from the linear curves, like I showed before. R = 1 is this sphere, which I also showed before, but I showed it, then I already kind of briefly mentioned that none of these, they actually thermalize it with this butterfly velocity. So they all, well, for these it's very clear. So they actually are not done at all. So they're not thermal at all at this point. They really need much more time to thermalize. But even the spherical one, it's actually, you can solve it analytically. So we know that it thermalizes slightly later, like 10 to the minus 3 later. You can also see it here. So 3 dimensions is a little bit less interesting for that reason, and that's why I want to spend my final 10 minutes on the real results, which is at 4 dimensions. So then what we did is we still wanted to kind of keep the same amount of symmetry. So that's also why I showed you kind of these practical computations. But okay, so if you go 1 dimension higher, you can of course take like a stadium like this, and you can rotate it either this way or the other way, and then you still have 1 rotational axis. So we can still the computational complexity is the same. You just get the Jacobian vector, and the Jacobian vector is just different from here to there. And these surfaces are also actually, in some sense, well, they're just rightly chosen. Because very interestingly, so this one, well, of course, when this side is 0, then it goes to the sphere. But if you take this ratio between the short axis and the long axis to infinity, then here you get a cylinder. And the cylinder you can also solve analytically. And has a pretty different solution to the sphere, but quite curiously, that also kind of motivated this conjecture even more. I already mentioned the cylinder also saturates the butterfly velocity. We call this ratio bigger than 1, and the other one ratio smaller than 1, but that's just the ratio between the short and long axis. It's just nomenclature. Interestingly, so if you take the ratio here to infinity, then of course it becomes like an enormous, like it basically becomes 2 planes. And then you were back at the stripe case, also kind of already shown, and the stripe case we know saturates an entanglement speed. So it takes more time for this one to thermalize, will be at least in the infinite ratio limit we know. Then to the results, I'll first do this one with the stripe, which we know that a very large ratio saturates later. So okay, so we look here at different times. So at first, indeed, so there's this linear growth, and the membrane is approximately straight, and the entanglement entropy grows with the entanglement velocity. And then you get like, okay, one reason also why I show this, you get this more kind of interesting. So here in the boundary is the stadium, but at the null shell, it's more like an ellipse. And you actually get some kind of cusps in the surface. So there's no derivative in the integral. So these cusps are actually perfectly allowed. And they do show up, but they actually don't show up on the surface at the shell. It's kind of something which I found relatively interesting. But okay, then you have these membranes and you integrate them and you get the entanglement entropy. And then here we show the entanglement entropy as a function of time. Here there's a zoom in of the big one. So the black dots are the numerical results. The blue line is just the thermal value. And you see here already that since these black lines are the numerical results, so you actually see that it thermalizes around here at like 1.42. So much later than actually 1 over the butterfly velocity, which we kind of expected, of course, because at least in the infinite ratio limit, where this one will be 0 instead of 0.4, then it has to thermalize at the entanglement velocity. But here it's somewhere in between, so that's quite consistent. But I also show you this plot because in the red line we actually have we have an analytical upper bound of the entanglement entropy. And the way to do this, and it's a little bit important to make our later conclusions also more robust, is to take, instead of taking the real surface, we take actually a cone surface. So just with constant angle, actually angle VB, butterfly velocity. And then at some time we switch it to a straight surface down. So it's an angle 0 and would be entanglement velocity, going with the entanglement velocity. So this is of course, well, in general would not be a minimal surface, and there's no reason to expect it. But since it's we're with a minimization problem, that particular surface we can compute analytically, and of course, since it's a minimization problem, this gives an upper bound. So you see also the red line is always above the black line. But quite interestingly, so we have this extra parameter T prime, where we switch from this cone-like thing to the straight thing, to the entanglement, to the butterfly thing. And well, since it's a minimization problem, we minimize over this T prime. It has to be within the bounds, but we can minimize it over it. And interestingly, so for this case, we actually have a little bit of an extra intuition. So we see here that at the butterfly velocity, that even with this analytical estimate, this T prime is non-zero. So you don't have so non-trivial, and that's why there's so the butterfly. If it would be a fully butterfly cone, there is actually the solution with the black dot, and that would then that would. But here we find that there's a different solution, which is a lower entropy, and since it's a minimization problem, this is preferred, and hence it thermalizes later. But this non-trivial T prime solution doesn't always exist. So and that's why we kind of later on will understand kind of that sometimes this starts to exist, and that's when you thermalize later, but it doesn't always. This is just to complete that picture. So what I just presented you is like for ratio 0.4. But you can do it for all kinds of ratios, and actually for the zero ratio, that's the stripe case, and it's the analytic case, so this is the dashed line. And you see that from the sphere to the dashed line, all these different ratios nicely interpolate between the solutions. Then perhaps the most interesting result is then the other way, the tube. And well, here I just show an example, and I show also the numerical results and the upper bound. In this case, the T prime is equal to well, so there's no part with this entanglement velocity. It's only butterfly velocity, and that's why the bound saturates at exactly 1/VB, and also our numerical results, even for this non-trivial ratio, saturate exactly at 1/VB. And you can here also see it in the shapes. They really go to like cone-like features with this characteristic speed or angle of the butterfly velocity. We did that, and of course also for more ratios, and also for the cylinder you can do it analytically. So that's the infinite ratio, and all our results lie in between, and they all exactly saturate at 1/VB. So we basically now found this generic class of scrambles which saturate at this butterfly time. So showing that this fast scrambling is really generic. And well, to summarize that a little bit is that, okay, of course, analytically known was that the cylinders, they saturate, and the spheres also, but the stripes do not. And the new result is then that there's this general class between the cylinders and the spheres, if you want, where the waffles, they don't saturate. The waffles are more like the stripes. Depending a bit on the ratio, we were sure about it from around 0.75. But these tubes, they always separated, and they make this bound generic. It's not a zero or the zero subset. And okay, to comment a little bit more about it, there's of course a crucial difference between cylinders and stripes, in the sense that stripes, they have two infinite directions, and the cylinder has only one infinite direction, much larger than R. So R the largest inscribed sphere. And so in that sense, it's somewhat intuitive that the stripes or the waffles, that they take longer to thermalize, because there's such a large space with all kinds of correlations to thermalize. So okay, so I already said also the charge spheres, they do not always saturate. So yeah, this really comes to the conclusion like that Schwarzschild black holes could really be the fastest scramblers for this generic type of things. And one thing I want to note is also that you can compare with free theory. And if you had like an infinitely large, well, so even for cylinders and for stripes, since there's an infinitely large direction, they would never saturate. They would never saturate at any time, because there can always be two quasi-particles which go in exactly in this infinite direction, and they would always keep a little bit of the entanglement in that region, and it would never really exactly thermalize. They would also always exponentially go to the thermal value. So it's really quite special that they exactly saturate at this time. Then to show a little, one more thing is that, well, okay, this is just, I mean, I think it's very intuitive, but we did this, we did also the same thing for ellipsoids. Then we don't have like the cylinder and stripe analytic estimates, but it's kind of very similar setup and very similar computation. And also there you see that the one with only one direction, like the cigar with one infinite direction, it really saturates, it's a butterfly velocity, and the other one saturates later. So that's very consistent. To to say, this is just like putting some pictures of a paper we had before also with Christian Ecker and collaborators, where we really look like at an entanglement entropy and kind of these kind of shock collisions and hydrodynamics and shock collisions. It's more like an outlook with something we're thinking about, and also how this membrane theory, like as a hydrodynamic theory of entanglement, originated in like these tensor networks, where really the idea is like, well, now everything is homogeneous, but actually this epsilon v, this action, can have hydrodynamic corrections, so it can slowly vary as a function of space, and that would be very interesting. So you could have a temperature which goes from slightly higher, slightly lower, and then you can so the whole framework should work also in that context. This is something we may be looking at. I'm running out of time, so to my last slide. Okay, so this thermalization beyond local equilibrium, thermalization of entanglement entropy we really looked at. This membrane theory is really nice because you look at the large time and length behavior, which is probably the interesting part anyway, and it really makes this extremal value problem to a minimization problem, which you can put in the service evolver. You get nice pictures, quite easy to solve. Well, the spheres and the stripes, they thermalize in the butterfly time, so spheres thermalize as fast as possible. Stripes slower, but then there's this. But then we solve this for this variety of shapes, or the generic classes of shapes which separate in the butterfly time. Yeah, so this excludes. Well, the last thing I want to say is that it's much more general than holography. The only thing from holography we put in was this epsilon v. So you can, if you give me a different function epsilon v from condensed matter, or you can even kind of in some sense measure it from like a sphere, for instance, you compute entanglement entropy for a sphere, you get epsilon v, then you can compute it for any other function using this service evolver. So there's also this epsilon v didn't originate from holography. So it's, in that sense, our results are very general and go much further than these examples I just shown. So yeah, that finishes the talk. Thanks.
Okay, thank you very much for your very nice talk. Any questions, please? Okay. Maybe I will ask questions. So, what is your feeling if we consider in general thermalization problem, like we take several material points and put them in the cube or in the sphere with the same volume? Where we expect more fast thermalization, in the sphere or in the cube?
Oh, that's a very nice question. Yeah.
Try this to perform this numerically. It's possible to study. This is just we consider some. We can take into account only direct interaction between these two, this material point. So
yes.
Maybe
yeah. So I
the answer already known for mathematician. I don't know.
So well, yeah, the cube, of course, we didn't do, but we could do that. And then, but the radius, okay, so in principle, the cube, since the radius is the same and it's a larger space, it could thermalize a bit later. But I think we're still in this class that you don't have like two infinitely long directions, which are really much longer than the other direction. So I think in this setup, it would really still thermalize in exactly the same time as the sphere. It would only be that if you have like if you have a bar, it would also always thermalize in the same time. It's only that if you have like a bar with two infinite directions, then you start thermalizing later. Of course, that's for ADS-Schwarzschild kind of membrane action. I mean, if you have like charge, then you can slow the thermalization down, and there's several other things to slow down the thermalization. But yeah, I think that's the answer. Like for bars, it's kind of you're still within the fast thermalization regime, and a cube is a special case of a bar.
Okay, thank you.
I have a question.
Please.
Generally speaking, it follows from your formula that membrane theory can be applied also not for entanglement, but for quite arbitrary observables that have geometric meaning. I mean, you can express, as I understand, you can express, for example, for correlators, Wilson loops, complexity, and other measures, right?
That's general.
As I remember, in the Nahum paper, they was trying to do in subsequent Nahum's paper, probably they was trying to make some non-entanglement circuit. But here it seems that if you can write down the geometric action, you can try to go to membrane, right? For observable, right?
Well, that's actually a good question. I didn't actually follow this from a holographic point of view. Like if you can, if it's like an extremization problem, then of course you can. But like for general correlators, it's not so clear that the same trick works, right? Although I guess you can integrate out the zeta and all these kind of things, so you get some kind of some kind of formula in lower, one dimension lower, and then in that sense you get a.
I mean, typically, for example, for an old paper by Honlu, you can write down quite a general geometric action, right?
Right. For what exactly do you mean?
I mean, you can write down. I mean, the geodesic, for example, in d-dimensional example, is also have also the same form, right? I mean,
yeah, and you have a 2-point function.
The codimension changes, right?
Yeah. Okay, exactly. So that's actually nice. But the geodesic you can already solve in the full problem, so then maybe the membrane is not really a simplification. But okay, I think I see what you're saying. So you can do this also for this is like codimension 2, and you can do codimension 3, and you can do this for other type of membrane actions.
Yeah, generally speaking, yes, I suppose. This work for general correlation functions. Okay, for example, non-local and local ones.
Yeah, for 2-point functions for sure, but for general, okay, yeah, it's a nice question.
I mean, 3-point function also should work, but it generally have to. You generally have to make one more extremization for a point in the bulk.
That's right.
Okay, I see. So,
yeah, I don't really know if that makes sense to try.
Okay. Thank.
More questions, please. Okay, if no more questions, let's thank the speaker again. Thank you very much, Wilke. Bye, everybody. Hope to see you tomorrow morning. Bye-bye.